Hi, I'm Justin Kay. I'm a third-year PhD student at MIT CSAIL in the Beery Lab, and I work on computer vision and machine learning for environmental conservation. And today I'm going to answer a few questions about my work. Okay, so the first question is, how is AI helping scientists monitor vulnerable ecosystems, restore endangered species to their habitats, and even address the effects of climate change? When we talk about monitoring the Earth's ecosystems in order to manage them, in order to protect them, usually this starts with collecting observations. And historically, these observations have been collected by humans. They go out into the ecosystems that they care about, and they write down what they've seen, and then they use this data to inform management policies or conservation policies. Our ability to observe those ecosystems at unprecedented scales has really grown in recent years. And so quickly, our ability to collect the data has sort of outpaced our ability to analyze the data. And this is where AI can really have a big impact. Usually we have very noisy input data. We might have video data, image data, audio data, and we want to transform that raw data actually into the insights that we care about. So into some prediction of what animals live there, how many there are, and how this is changing over time. You can imagine that once you have a model that can predict output variables pretty well, given some environmental observations, now you can do forecasting and simulation and try out different scenarios that might be able to inform how you take action to manage these ecosystems moving forward. Okay, so next question is, with so many AI models available to analyze wildlife or ecosystem data, how does your research help conservationists pick the right one for a specific task? So this is one area where the landscape of working with AI models is really changing. You no longer really have to train your own model to start getting predictions on data that you've collected. There are now large open source repositories of pre-trained models, and you can just go and download one that has the capability that you want, run it on your data, get the predictions that you need to do the downstream science or conservation that you need to do. The problem, though, is that there are so many models out there. How do you choose which one to use? This can be a very time-consuming process, especially with real data, especially with conservation data, where you may have very imbalanced distributions in your data set of the things that you care about. It may be very sparse. Models may perform differently on different subsets of your data. And so it can take quite a while to generate a really representative test set of the thing that you care about. And so what we've been working on is what we call an active version of this problem, so active model selection. And the idea is that we've made this process interactive. So rather than you going out and in bulk annotating a test set for your problem, we use the models that you're considering to tell you which data points are most informative for differentiating the candidate models. And so by doing this, we've come up with a framework that we call CODA, Consensus-Driven Active Model Selection, that across 26 different benchmarks that we curated was able to reduce the annotation effort required to find the best model out of your candidates by over 70%. Okay, so next question. Before coming to MIT, you co-founded AI Fish, a company that develops computer vision algorithms to track and annotate fish data. What inspired you to return to academia and research? So AI Fish, which is still currently in operation, is a company that builds computer vision and machine learning powered software for fisheries monitoring and ocean conservation. In fisheries monitoring, they've started deploying cameras on board these commercial vessels to collect data at sea and get kind of the fine-grained details that they need to set fisheries management policy. And so cameras kind of offer this opportunity to collect and analyze data from more boats than you ever could by deploying human observers on board each boat. But you run into the same data analysis bottlenecks. And so at AI Fish, we built computer vision powered software to drastically speed up this video review process, using computer vision to sort of automate the species identification process. In trying to build a real product based around computer vision, one thing that I started to notice is that in many ways, the algorithms and the software and the interfaces were all being developed kind of independently. And there was an awkward amount of glue that had to happen to put all these pieces together. And in some way, it felt like it would be better to take more of a holistic view and think about how you could develop algorithms and software and interfaces all together to inform each other and to create really systems that from the ground up take into account the fact that they are dealing with probabilistic predictive models. This challenge is part of what inspired me to go back for a PhD, is it feels like there are more fundamental challenges with how we think about computing in general from kind of an AI first perspective. One thing that I'm excited about in doing a PhD is getting to come back and think at kind of a meta level about certain problems and address what are kind of the fundamental limitations of current computer vision and machine learning algorithms, and take kind of a longer time horizon in terms of focusing on problems that aren't going to be solved tomorrow, but if we can solve them, could have much longer term impact than just solving application problems kind of one by one as they come in. Okay, so next question. When applying AI to science and conservation, what are the biggest challenges? And what does it mean in your work for an AI system to be truly deployable for field scientists or practitioners? So I think one big challenge here that most people face when they're developing methods that they want to deploy in the real world is the big gap often between what you observe in the lab as you're developing your model and what you observe in the real world once you've deployed it for actual use. And there's many reasons why this gap exists. One is evaluation. Often you're not quite measuring the right thing in your bench testing. So maybe you're looking at a test set that is from a particular data distribution, and then in the real world you encounter a completely different or even slightly different data distribution that completely changes the outputs of your model. And so if we start thinking about scaling up observation with machine learning, now we have predictions that we know are imperfect. And so the interesting research question there is, can we take those imperfect predictions and figure out how to best incorporate them into the statistical modeling that we're already doing in a way that can give us more accurate and more fine-grained information about the ecosystems that we're studying? Okay, next question. Evaluating machine learning models on real data is notoriously hard. Could you explain some of the key obstacles, such as distribution shift, and how they play out in real conservation applications? Machine learning models are really good at finding patterns in data. And so if you've collected some data set that is representative of the thing that you want to predict, you can fit a machine learning model to that data distribution, and it's going to perform very well in the future on data that comes from that exact data distribution. The problem, though, is that often data distributions are changing over time. So what you trained your model on might look quite different from actually the data that you collect out in the real world once you've thought about deploying your model. Often the data distributions are changing at a rate that you couldn't even collect this training data and retrain at the rate that you need. And so one thing that we've been working on is machine learning systems that can automatically adapt themselves to changing data distributions. So what that self-supervised task might look like is making sure that your predictions are consistent across some transformation to the data that kind of makes sense for your application. And so by doing this, we were able to come up with a fish detection system that can now adapt itself continually over time and show the ability to recover from performance degradation that was caused by distribution shift. Okay, next question. Could you tell us about some of the other ongoing projects at your lab? For example, using drones to keep an eye on coral reefs and applying multimodal Earth observation data to monitor ecosystems. Absolutely. So I'm in Professor Sarah Beery's lab in CSAIL. We have a number of PhD students and postdocs in the lab, so I'll kind of try to go through alphabetically and say what everybody's working on, because everybody's doing very cool stuff. Antoine is working on re-identifying elephants in imagery. So this is trying to identify the same individual over time. Elena and Lauren are working on trying to predict biodiversity variables from remote sensing data, so satellite imagery. Julia is working on ways to optimize computer vision algorithms to focus on the things that we actually want them to focus on versus spurious correlations like background features. Neha is working on data-centric approaches to dealing with distribution shift. And with Kai, we're working on more sophisticated approaches to video understanding, specifically focused on fisheries data. Rupa is working on computer vision techniques for monitoring coral reefs with drones, specifically on techniques for kind of removing some of the warping that you get from the water. Tim is working on using multimodal remote sensing data and on-the-ground data for enhancing statistical ecological models. And with Tim, we're working with an undergrad, Ada, who is working on incorporating noisy machine learning predictions into statistical ecology models. Okay, next question. You've designed computer vision systems to count migrating salmon in underwater sonar video. What are the implications for understanding those fish populations? We're looking at how many salmon migrate each year upstream to spawn. So this is a very important question for managing salmon populations, both for fishery management as well as for conservation. The way that people typically collect this data is they often have to camp out at the very remote site and count the fish in real time as they observe them on the computer monitor. And so while this is pretty accurate, it doesn't scale very well. And so we've been working on computer vision-based techniques to automate some of this counting and to make the data review process much more efficient for them. And so recently we've had a really exciting deployment with the Klamath River Dam Removal Project. And we've been working with them, transferring models back and forth, fine-tuning them for their use case. And they're actually using our models in deployment right now to count the salmon. And it was pretty amazing. They observed salmon come back within a week. Okay, so now we have a question from the MIT CSAIL social media followers. You developed CODA, an approach that helps scientists determine which AI model to use on a particular dataset and reduce the time needed to process it all. How does CODA handle environments with multiple species or datasets whose underlying conditions are shifting, for example, because of climate change? Have you seen performance differences across different ecosystems? Each of these models actually kind of tells you something different about the data that you have in hand. And so in some sense, you can use the wisdom of the crowd, where the crowd is your set of models, to tell you something about this data in a way that allows you to then decide which model is the most accurate. And so the way that we do this is we kind of pool all the predictions from all the models, come up with kind of a consensus vote, and then use that consensus to give a prior on what we think the accuracy of the different models might be on your data. You start to learn the different strengths and weaknesses of different models and how they perform on certain classes versus others. And so we've observed that CODA actually works quite well across many different studies, many different ecosystems, and even under distribution shift, it's able to identify models that perform best under the given distribution shift. And so the exciting thing about working on active model selection in this context is it lets you think about kind of the end-to-end machine learning development and deployment lifecycle and start to ask, okay, where and for what reason should we be collecting human annotations, and how should we best use them to get towards solving the predictive task that we actually want to solve? All right, we've got one more question from the audience. How did you first get started in this field, and what advice would you give someone today who wants to enter the field of AI for conservation? Yeah, this is a great question. The opportunities are kind of changing all the time. I got started by founding a startup. You know, you don't need anybody's permission to just start working on problems. If you can find someone who has a data problem in their environmental work, and you can start working with them on ways to address it, that can open a lot of doors. For me, it allowed us to then apply for grants that helped us get the company off the ground. But for somebody else, it might lead to other job opportunities, research collaborations. It could eventually lead to getting a research position if that's what you want. It's not always obvious how to just immediately get a full-time job to work on this kind of stuff, but I would encourage you to just start working on something. Start working on a side project or some kind of collaboration, because you never know where it could lead. Get your foot in the door. And if you want to work on AI for conservation, it's one of the most supportive communities out there. And I would say just go for it. Okay, that's all the questions we have. Thanks everybody who submitted questions. It was a pleasure answering them. If you'd like to keep up with my work, you can find me at justink.github.io. And if you have any further questions, please feel free to contact me. I look forward to talking to you.